Hi everyone, we're starting chapter 16 on exponential functions and logarithmic functions and the rules of logarithms. So the first thing we're going to do is we're going to take a quick look at reviewing several sections of chapter 16 which we've looked at last year, and we're going to be reviewing the rules of the exponents, of rational exponents, of factoring with exponents, and also multiplying and so forth with exponents. Alright, and powers. Alright, so the first thing is we're going to look at rules for the exponents. So we should all remember by now that when we've got two bases that are the same, and we are multiplying two bases that are the same, and they have a power to them, the powers are going to be added. So for example, a to the m times a to the power of n would equal a to the m plus n. So an example of that would be x squared times x cubed, which would give me x to the power of 5, because 2 plus 3 is 5, and with multiplication we add our exponents when our powers are the same. Likewise, if we've got division of equal bases with powers on them, then that means we're going to be subtracting the powers. Therefore, x to the 6th divided by x to the 4th would equal x to the power of 2, because 6 minus 4 is 2. Now, the third example is a power to a power rule. The power to the power rule is the one that I think is most confused by students. And the power to the power rule just says that if I've got a base that's raised to a power, but it's raised to another power as well, then those powers are going to be multiplied. So it's like as if I were doing x to the 4th raised to the power of 3. Well, if I expanded that, that would become x to the 4th times x to the 4th times x to the 4th, which would take me to 4 plus 4 plus 4, which gives me x to the 12th. So I used the first rule. However, because we can't do x to the power of 4 raised to the power of 20, for example, and write that out 20 times, what we do is we take a shortcut and we multiply it so that we say 4 times 3 equals 12. And in this case, x to the 4th raised to the power of 2, in the example up above here, is going to be x raised to the power of 8. Now, if we have two bases, so if we have two bases in the next rule, if we have two bases that are raised to the same power, we are going to then multiply each base out by that power. So for example, AB raised to the power of m will go to a to the m times b to the m. And therefore, xy to the power of 3 will go to x to the 3rd, y to the 3rd. And likewise, with division, the same thing will occur. We'll have two different bases that are raised to the same power. That means that everything will have the same power on it. So it will go to x cubed divided by y cubed in this example. Now, the next rule is a to the negative m. So when I have a base raised to a negative power, what we do is we place it over 1 to turn it into a positive power. So therefore, a to the negative m will become 1 over a to the m. Therefore, 2 to the power of negative 4 will become 1 over 2 to the power of 4, which when it is expanded, it will go to 1 over 16. Our next rule is a to the power of 0. Anything raised to the power of 0 will always give us 1. So that 2 to the power of 0, x to the power of 0, or 1/2 to the power of 0 will always equal 1. And our last rule is a over b to the power of negative m. And what that basically tells us is that if we have, again, a fraction, though, that is raised to a negative power, what you can do is you can flip the fraction around simply in order to turn it into a positive fraction. So what that means is that if I had 2a over 3 raised to the power of negative 2, I would flip it over to turn it into 3 over 2a, and my power would go to the squared. And then I would just proceed to multiply out and expand. 3 squared is 9, and 2 squared is 4, and a to the power of 2 is just a squared. And that would be that. All right, so that would take care of section 16a in your textbook. So we're just looking at the laws of the exponents. In section B, we are looking at fractional exponents. So when we have a fraction as an exponent, how do we go about simplifying or solving it? So the rule that we use is a raised to the power of m over n. That means that if I have a fraction of m over n, it means that I am taking the nth root of a and I'm raising it to the power of m. So an example of that, just to show you, would be something along the lines of x to the 2/3 if I had to rewrite that in radical form. So I can go back and forth between writing it in exponential form and in radical form. And in radical form, this would be the cube root of x raised to the power of 2. X to the 1/2 would be the square root of x raised to the power of 1. But normally, anything raised to the power of 1/2 just means the square root of. So anytime I see something raised to the power of 1/2, it automatically means the square root of. And that's because I'm taking the square root of whatever's under the square root sign, and it's raised to the power of 1. Now, if I were to look at x to the power of 1/4, that means I'm taking the fourth root of x, which is raised to the power of 1, and essentially that means the fourth power of x. I don't need to put the 1 because it's irrelevant at this point. Okay, so if we were to do the multiplication of like bases, but we had powers that were fractions, then that would mean that if I am multiplying, I would have to add them. And adding the fractions means that I need to get common denominators. So for example, x to the 1/2 times x to the 1/3 would mean that I would have to do x to the 3/6 plus 2/6 for x to the 1/3, which would just end up giving us x to the 5/6. And if I were to rewrite this, normally we just leave it as a fraction, but if I were to rewrite this as a radical, this would actually be written as the 6th root of x raised to the power of 5. We need to be able to go back and forth. So I should be able to go from the 4th root of x back to its original x to the power of 1/4. Now, if I were to evaluate, for example, these next 3 questions, evaluate is asking for an actual number answer. So I would be using here more than one rule to work this out. So I would start by saying 1 over 32 to the power of 2/5, because I do want to get rid of that negative. And then the next thing that I would write out would be 1 over the 5th root of 32 raised to the power of 2. And the answer that I get from that is, well, what number multiplied by itself 5 times is going to give me 32? That number happens to be 2. And when I take 2 and I square it, it becomes 1 over 2 squared, which will go to 1 over 4. If we look at the next question, we have 8 over 27 raised to the power of 2/3. Well, what that means is that we've got the third root, or the cube root, of 8 over 27. So what we are going to be taking is we'll be taking the cube root of both 8 and 27. So the cube root of 8 goes to 2, and the cube root of 27 goes to 3. That's our final answer. So it's 2/3. Now, if we look at the next case, which is a bit more specific and a bit more difficult, we've got 27 x to the 9th, y to the 3rd, all divided by the square root of 4x to the 4th, y to the 4th. Well, the denominator part of this is easy to resolve, in that the denominator simply asks that you take the square root of 4, which is 2. The square root of x to the 4th means that you're doing 4 divided by 2, which is 2. Sorry, x squared. And you're doing y to the 4th divided by 2, which goes to y squared. Up in the top, we've got 27 to 27 means that we're looking at for the cube root of 27, and the cube root of 27 is what number multiplied by itself 3 times gives us 27, and that number is 3. We then take the x to the power of 9 and divide it by 3, and that gives us x cubed, and then y to the power of 3 divided by 3 gives us y to the power of 1. Now, the last thing that's left for us to do is to simplify the x's and y's so that we have x cubed divided by x squared gives us an x up at the top, and y to the 1 divided by y to the power of 2 gives us really y to the negative 1. It's 1 minus 2. But because we don't want to have a negative in the denominator, we're going to place it as 3 over 2y with the x up above. Alright, so this is all review from last year. Alright, so let's just do a very quick review of a couple of expressions. We'll just do this first one. So if I have a to the power of 3 over 2, so a to the power of 3 over 2 divided by b to the third, I'm going to multiply it by b squared over a to the power of 1. Now why did I do that? Because it's a division sign here up above. Let me change the color of that. It's a division sign, and because we've got a fraction, we will change the we will change the second fraction, and we will multiply by its reciprocal. Now, when we are multiplying by its reciprocal in this case, the a to the negative 1, by the way, the a to the negative 1 does not change its position. It doesn't change to a to the power of 1, but it goes to a to the negative 1. I made an error before in not putting the negative 1. So it stays the same, because what my goal was right now was just to flip over the fraction. I flipped over the fraction, and now I'm going to bring the a to the negative 1 back up to the top. So we have a to the 3/2 times b squared times a to the power of 1, all divided by b cubed. So a to the 3 over 2 plus a to the power of 2 over 2 will give me a to the power of 5 over 2. And now I've got b squared divided by b cubed, which will give me a b to the negative 1. Now, that b to the negative 1 is going to be brought down in the denominator to turn it into a positive. So it becomes a to the 5/2 all divided by b, or b to the 1. All right. Let's take a look at the next section, which is exercise 16G, where we are looking at exponential equations. So when we're looking at exponential equations, what we are trying to do, or what our goal is that to bring everything, as you can see, our exponents have the unknown x's up there. They're not down in the base. So our goal is to try to figure out what our value of x is in the exponent. So what we need to do is we need to bring everything down to the same base, because the rule said that we looked at last year, it was if a to the n equals a to the x, for example, then that means that we can forget about our bases and just say that x equals n. So when we have bases that are the same, then we can forget all about the bases and just concentrate on what was in the numerator. Sorry, not in the numerator, in the exponent. So let's take a look at this first example. We've got 2 to the x plus 1 is equal to 8 to the 2x plus 3. Well, I can rewrite 8 as 2/3 to the power of 3, but that is raised to the power of 2x plus 3. So now that my bases are the same, I can cancel them out, and all I have left is x plus 1 is equal to 3 times 2x plus 3. Now I'm just going to move this over here, so that we can now say that x plus 1 is equal to 6x plus 9, and we get a common denominator. I'm going to bring my 9 over to the left, my x over to the right, so we have 1 minus 9 equals 6x minus x, and negative 8 is equal to 6x, and x is equal to negative 8 over 6, which when divided by 2 becomes negative 4/3. So there's my answer to the first problem. The first problem is the value of x has to be equal to negative 4/3 in order for the left-hand side of the equation to be equal to the right-hand side of the equation. Now, if I want to solve the second question, here we have 1 over 9 x to the raised to the power of x plus 1, and that equals 27 to the power of x. So what I want to do is I want to bring everything down to the same base, and the lowest base is the prime number base that I can get to, and in this case it would be 3. So if I rewrite 1/9 as 3 to the power of -2, and then that gets raised, and that gets raised to the power of x plus 1, that'll equal 3 cubed times x. And now this will end up giving us 3 to the -2x minus 2 is equal to 3 to the 3x. Our bases can be cancelled out now because we do have a one-to-one relationship going on both sides of the equal sign. And so we have -2x, so that we have -2x minus 2 is equal to 3x, equals 3x, and therefore -2 is equal to 5x, so that x is equal to -2/5. My last example that I'm going to show here is 1 over 125 raised to the power of 1 plus raised to the power of 1 plus 2x. So I'm going to rewrite 1 over 125 as 1 over 5 cubed raised to the power of 1 plus 2x. And that'll equal 5 squared raised to the power of 3x plus 2. Now again, I got a common base of 5, but I need to bring this one up to the top so I don't have 1/5 on one side and 5 on the other. So that this will become 5 to the power of -3, and it's 1 plus 2x is equal to 5 to the 6x plus 4. We now have the same bases. We can cancel those out, and we end up with -3 minus 6x is equal to 6x plus 4. So I'll bring -3, -4 equals 12x, so that -7 equals 12x, and x equals -7/12. So it's not always necessary to have whole numbers as answers. As you can see, all of our answers here thus far have been all fractions. Okay, moving on. We can take a look at, let's look at the second example here. So we've got 8 times 2 to the power of x plus 1 equals 2 to the square root of 2x. All right, so what I would probably do at this point is I would get rid of this 2 and this 8. So I would bring the 2 over to this side, and I would turn it into 4 bracket 2 to the power of x plus 1 is equal to 2 to the power of x raised to the power of 1/2. Okay, so now 4 can be rewritten as 2 squared, and that would be multiplied by 2 to the x plus 1, and that equals 2 to the 1/2 x, or x over 2. Now, because these are multiplications, I don't multiply, though, 2 times x and 2 times 1 here, because I still have the base. So what I do end up doing is I end up saying 2 to the x plus 1 plus 2 is equal to 2 to the 1/2 x. So this goes to 2 to the x plus 3 equals 2 to the 1/2 x. And now I can cancel out my bases, and I have x plus 3 equals 1/2 x, so that I have x minus 1/2 x is equal to -3, and I have 1/2 x is equal to -3, so that x equals -6. Okay, let's try looking at perhaps the next one, which is 9 to the power, 9 times 3 to the power of 3x plus 1 equals 1 over 9 to the power of x. Okay, so we've got 9 times 3 to the 3x plus 1. Oops, forgot to put in 3x. 3x plus 1, and that equals 9 to the -x. All right, so if I rewrite this 9 out as 9 to the 1, then that's really like saying 3 squared times 3 to the 3x plus 1, and that equals 3 to the negative 2x. Alright, so now what I need to do is I will do 3 to the 3x plus 1 plus 2 is equal to 3 to the negative 2x. Our bases are the same. 3x plus 3 is equal to negative 2x. Bring this over to the left-hand side so that we have x equaling negative 3. It's obvious that we can check the solutions to these by actually replacing negative 3 back into the original questions, and if our left-hand side equals our right-hand side, then we know the answer is correct. Okay. The last thing we're going to take a look at is exercise 16H. I know we've gone through a lot of sections in one, so we're going to be looking at section 16H, expansion and factorization of exponentials. So if we take a quick look at expansion, you'll recall that when we expand, we can do it by using the distributive property, like 2x plus 6 in this case, or by using FOIL. In this case, it would be x squared minus 3x plus 2x minus 6, which gives us x squared minus x minus 6. Or we could use a difference of squares, as up here in the corner on the right, which would be x squared minus 4, because we have identical binomials, and the only thing that differs is one is positive and one is negative. And then we have the perfect squares, so this was difference of squares up here. This was FOIL. This was just simple distributive property. And the last section being perfect squares, where we square the first, we square the last, we multiply everything inside the parentheses together and double it, so that we get that answer. And these are perfect squares. Now, if we have to apply this, though, to exponentials, the story becomes a little bit more complicated. Not impossible, but a little more complicated without any doubt. So that we would have, for example, using the distributive property here, 2 to the x times 2 to the x. Well, that gives us x plus x, which is 2 to the 2x. And then 2 to the x times 1 just gives us 2 to the x. That's done. It's expanded. Now, if I want to do 3 to the x, now if I take a look at this, I analyze it first, and I determine that it is just a FOIL question, so I'm going to have to FOIL everything out. Then it'll become 3 to the x times 3 to the x will give me 3 to the 2x. 3 to the x times 2 is not going to give me 6 to the x. 3 to the x times 2 gives me 2 times 3 to the x. That 2 does not have an exponent on it, and therefore I cannot multiply the two bases together. Okay? It is not possible. And if I do 1 times 3 to x, that just gives me 1 times 3 to the x, and then my last is just 1 times 2, which is 2. So my final answer turns out to be 3 to the 2x plus 2 plus 1. So this is acting, the 3 to the x is acting like as if it were a variable. It would be like saying 2a plus 1a. So this gives me 2 times 3 to the x plus 1 times 3 to the x gives me 3 times 3 to the x, and it's plus 2. So here you have to be really careful. Okay? And the third example that I have here is one where we're looking at a difference of squares. So all I have to do is square the first. 2 to the x squared gives me 2 to the 2x. And I square the last, minus 16. Finished. And actually, I don't need parentheses there. I'm trying to remove them. Okay, so the second one seems to be the one that's most troublesome, I would think. So let's try to do an example, all three of these examples actually. So if we do all three of these examples, so 2 to the x times 2 to the x will give us 2 to the 2x. And 2 to the x times negative 3 will give us minus 3 times 2 to the x. Okay, so it's times 2 to the x. Here we have perfect squares. Now, if you're uncomfortable trying to use perfect squares right now, then you are I encourage you to use just FOIL. And I may just use FOIL again here just to show the process. So 7 to the x plus 7 times plus 7 to the negative x. So that we've got 7 to the x times 7 to the x gives us 7 to the 2x. 7 to the x times 7 to the negative x gives us 7 to the 0, because x minus x is 0. 7 to the negative x times positive x gives us another 7 to the 0. And then 7 to the negative x times 7 to the negative x will give us plus 7 to the negative 2x. Now, our final answer will turn out to be 7 to the 2x plus 2, because these add up to 1 and 1, plus 7 to the negative 2x. That is our final answer. And if we were to place this in the order such that we have no negative exponents, then it would be 7 to the 2x plus 2 plus 1 over 7 to the 2x. All right, and then again here we've got another perfect difference of squares. So 2 to the x, all squared goes to 2 to the 2x, and then minus 25. Done. Oops. All right. The next section that we're going to look at, and last section we're going to look at, is the factorization. So when we factorize, maybe we should go back a page. As you can recall, factorization means that we are putting the parentheses back into the expressions, so that, for example, if I had 2x plus 6, I would remove my common factor here in factorization, take out a 2, and I'd be left with x plus 3. And just like if we had x squared plus 10x plus 25, I would notice that this is a perfect square, or I would see that two numbers multiplied that give me 25 and added give me 10 are going to be x plus 5 times x plus 5, or the perfect square, x plus 5 squared. Now, so these are all forms of factorization. Now we're going to do this factorization with exponentials. So what we want to do is we want to separate wherever we have a base with an exponent that has a plus or minus in it. What we want to do is we would like to separate them, so that this really becomes 6 to the n times 6 to the 1 plus this 6 here. Now, what we have in common now that can be removed would be a 6. And what's left over inside the parentheses would be a 6 to the n plus 1, because this is a 6 to the 1 and that's a 6 to the 1, and therefore we've taken it out, we've removed it. Now, the other question, which definitely part B is going to be far more difficult, is factorizing with exponentials, because they are not so easy to recognize. However, as soon as I see that I've got something like a 4 to the x and a 2 to the x, or I've got a 3 to the x and a 9 to the x, something that has perfect squares in them, okay? What I notice is that this looks like it could be a perfect square, and what I go ahead to do now is I go ahead and I say, well, 4 to the x really could be written as 2 squared x, or 2 to the 2x, okay? So this could be 2 squared, really, to the power of x, or we could call it 2 to the x all squared. And that's plus 10 times 2 to the power of x, and that's plus 25. Now, if you're able to see this, this is really like saying 2 to the x plus 5 times 2 to the x plus 5 factorized. Now, some people can see it, some people can't. The alternative way, so some people can see this very quickly and they can figure it out. But if you can't figure it out, the alternative way that you could go about doing this is to say, well, if I break down the 4 to the x to 2 to the x all squared, so you've got 2 to the x and 2 to the x here for both, then I could say, well, let a equal 2 to the power of x, so that wherever there is an a and 2 to the power of x, I'm going to replace it with a. so that I can say, well, I've got an a squared plus a 10a and then plus 25. And here it should be visible that I've got an a plus 5 all squared. The only difference being now is that I'm going to have to substitute 2 to the x for a, so that I put the 2 to the x back in, and therefore my answer goes to 2 to the x plus 5 all squared, or 2 to the x plus 5 times 2 to the x plus 5. You see that we have the same answer. The only thing that I did was I used a form of substitution where I got rid of the 2 to the x for a moment. I replaced it with just a single variable, a, but it turned out to be a squared plus 10a plus 25. And from there I was able to determine that it was a perfect square. Okay, the third example that I've got here is, again, another one that's a bit more complicated. And this one requires you to remember a specific rule. I've been talking too much, and I'm starting to stutter. Okay, so this requires a specific rule. And this rule here says that, if you can remember, we said that if we have a times b raised to the power of n, that means that these both have the same power. That works also the other way around, so that if I have a to the n times b to the n, well, it goes to a times b all to the power of n. So I can take the 6 to the nth, okay, and I can break it up into simpler terms, where perhaps there is a 3 to the n involved. So I can say 3 to the n plus, now if I change this to 3 to the n times 2 to the n, okay, and I divide that all by 3 to the power of n, I can now remove a common factor from the numerator here, which is 3 to the power of n. And what I'm left with is a 1 plus 2 to the power of n, and that's all divided by 3 to the power of n. Now, the 3 to the power of n here are multiplied. It's a product of terms here, so that 3 to the n and 3 to the n cancel themselves out, and your answer turns out to be 1 plus 2 to the power of n. Okay, here are our last two problems that we're going to simplify. And we've got 3 to the n plus 2 minus 9. So in simplifying this, we're going to do 3 to the n times 3 squared minus 3 squared. A common factor to remove here, simplify, or rather, this shouldn't say simplify, pardon me, but this should say factorize. Okay, so that we can remove a 3 squared here, and that leaves us with a 3 to the power of n minus 1. And there's really nothing more we can do there. Now over here, I've got a 49 to the x and I've got a 7 to the x. Well, 49 could be rewritten as 7 to the x all squared. Oops. 7 to the x all squared minus 4 times 7 to the x plus 4. And so this really is the same thing as saying 7 to the x minus 2 all squared. Now, this is taking the shortcut method being you either see it or you don't. Okay? But if I were to do it the other way, then I would say, well, what if I let a equal 7 to the power of x? Then this whole equation up here would become a squared minus 4a plus 4. And when I use sum and product here, I see that the two numbers that multiply together that give me 4 and added give me negative 4 are negative 2 and negative 2. So it would go to a minus 2 all squared. Now, because a is replacing 7 to the power of x, then I'm going to replace now back in 7 to the power of x in for a. And there's my answer, 7 to the x minus 2. Okay, I think this video was long enough, but it needed to be done. See you next time.